Okay, let's do number 35 on page 358. This is chapter 11. And here's the problem. We got this big wooden block here, and a bullet of mass little m hits it with a velocity v. And we want to know what is the angular momentum of the bullet block system. And what is the fraction of the original kinetic energy that's lost in this collision? Now that's probably where you're having the most problems, is figuring that out. Okay, so let's do the problem. So here I've got the where is it? Somewhere around here. I've got my given, find, and solve all ready to go. And so, well, the angular momentum, look, think of this as a linear momentum problem. When the bullet hits the block is also kind of hitting the bullet, right? They apply equal and opposite forces to each other. And so if this is my system right here, those equal and opposite forces apply equal and opposite torques to the system. So there's no net torque in the system. So there's no change in angular momentum before and after the collision. So L, I could just look at the look at this before it's hit, just before the collision. L equals R cross P. Okay. Now, but in this case, what's R? R is L. What is P? Well, it's the mass of the bullet times the velocity of the bullet. So it's mv. You good? Now, times the sine of what angle? But what angle is this? We said it's hitting, I think it said in the problem that it's hitting perpendicularly to L. So it's just the sine of 90 degrees, which of course is 1. And the direction of this, well, if I go R cross P, it would be in a downward direction. So, but we don't really care that much about the direction of it. So let's just worry about the magnitude of these guys. So it's just going to be LMV. So that's my answer for A. LMV. Right? Is that the answer in the back? Did you check that? Yeah. So that part is pretty easy, I think. But you have to know a couple things. You have to know that there's no loss of angular momentum in a collision like this for my system, because this is a closed system. So any torque that's going to change the angular momentum of this has to come from outside the system, and there isn't any. This is a frictionless thing, and you know, so we're just going to assume that there's no outside force, no outside torque. So that's my answer for part A. Now part B, what is it asking for? It says, what fraction of the original kinetic energy is lost in the collision? So what fraction is lost? Well, the amount of kinetic energy that's lost is really delta K divided by K. Okay, or K initial. So K initial, this is how much kinetic energy I had at the beginning. And then what I have to do is figure out what delta K is, and then I have to take the ratio. What fraction of my original was lost? So you express it as a fraction like that. Okay. So what's the initial kinetic energy of my system here? What is it? Before the collision.
No, 0.
No.
Oh, 1/2 mv of the bullet.
Yes, 1/2 times the mass of the bullet, little m, times that original speed, v, squared. Now we have to figure out what the final, the final kinetic energy is. Well, in order to do that, we have to figure out what the final, the final kinetic energy. We have to figure out what the final velocity of this is. Okay, so Now I know what the angular momentum is of this guy here. It's LMV. But so we have to figure out what omega is. Now, here's how I'm going to do it. There's multiple ways of doing this problem, but the initial angular momentum is going to be equal to the final angular momentum. Well, the initial angular momentum was LMV, but we'd like to express it in terms of, and by the way, what is this V? Well, I'm sorry, never mind. Let's figure out what the final angular momentum is. Well, the bullet has been lodged in the block, right? And it's got this final velocity. So we'll say that this is the final angular momentum is R cross P. So that's going to be L. But what's the mass now? M plus the mass of the block. Yeah, I'm just going to call it big M. Okay. Times V, I'll just call it V final. That's the final velocity of this block. So the initial angular momentum equals the final angular momentum, right? So this is my initial angular momentum. But after it's wedged in there, we've got this, it's the same L, and we have this mass times velocity. Actually, and another way of thinking about this is that you can think of this in terms of linear momentum as well, that P initial equals P final. So mv equals m plus m times v, because the L's cancel, don't they? So v final, the final velocity of my system, is going to be equal to m, just divide both sides, over m plus big M times my initial velocity. Does that make sense? So now I know what my final velocity is. Well, let's figure out what delta K is. It's K final minus K initial. Well, K final is 1/2, and what is it? All the mass is moving, and K final, the mass of both of them, so it's m plus big M, times the velocity, this final velocity squared. Well, what's the final velocity squared? It's this squared, which is going to be m squared over little m plus big M, quantity squared, times the initial velocity of the bullet squared. So this is my final kinetic energy. It's kind of awkward, but it's actually going to simplify quite a bit.
You didn't include the inertia of the, like, IW squared, I omega squared?
We could have done it that way. We could have, but see, I canceled out the L's, so that's not really a part of it anymore. We could do it with I, rotational inertia. Remember, these are particles, though, that are far away, so it's mr squared is the rotational inertia. And if you do it that way, it ends up reducing to this. In fact, that'd be kind of a useful exercise, is actually do this with rotational kinetic energy instead of linear kinetic energy, but you're going to get the same answer. Now, what's the initial kinetic energy is 1/2 m v squared, and then to get the ratio that they want, you divide by the initial kinetic energy. And what is the initial kinetic? 1/2 m v squared. Now we got some stuff that cancels out. This looks horrible, but it's really not too bad. We got stuff that cancels out. This m plus m and this m plus m squared, right? That goes away. And look at what I've got in each of the terms here. I got an m squared, an m, and an m. So that goes away. What else is in every term? The 1/2 goes away. And oh, all I need to do now, oh, and what else is in there? B squared is in every term. So it goes away. Oh my goodness. So what have I got left? I got m over m plus 1. Do I got room on my paper? Yeah, I do. I got m over m plus m minus what? 1. Now, you could leave it like that, but the book isn't going to leave it like that. Okay? What it's going to do is it wants to put a common denominator here. So let's simplify this a little bit more. That's going to be equal to m over m plus big M minus m plus big M over m plus big M, right? That's 1. So this is going to be m minus m plus big M all over m plus big M. Right, got common denominator now. Now m minus m is 0, and then you have so this is going to be negative m over m plus big M. Or this is the mass of the block divided by the mass of the block plus the mass of the bullet. Well, what does this negative mean? Why is it a negative ratio? Because what is true about delta K? What's true about my kinetic energy?
Okay. Oh, your initial equal or is more than your final.
Yeah, we're losing kinetic energy, right? Our final kinetic energy is going to be a lot less than my initial kinetic energy. So the numerator turns out to be negative. So the fact that we got a negative there, that's a good thing. Okay? And in fact, that's the fraction we're going to lose. So it's pretty messy. It is pretty messy. And there's multiple ways to do it. Now, you were talking about angular, rotational inertia and all that. Remember that these are particles, and that the rotational inertia of these particles, I initial for this system, the initial rotational inertia of this system is just the rotational inertia of this mass, which is mr squared, which is ml squared. The final is going to be m plus big M L squared. And so when you do the in terms of rotational kinetic energy, the L squareds cancel out. And the math turns into the same thing. But it would be a good thing to go through that. Also, I want to encourage anybody who's watching this now, including you, is to, now that you've seen this problem, wait a day and come back and try to work the problem tomorrow, okay, without looking at the video. And if you can do it yourself, ooh, I got it, okay? That's all.